All right, we're going to start off looking at part B to the question we were working on in the previous lecture. We had a little cockroach that we kind of figured out what its respiration rate is. It's this many moles of oxygen consumed over this many grams of our cockroach. So we're still dealing, I believe, with the same cockroach. So it escapes, or excuse me, let me get that back. It escapes, but it is caught by a child and is put in a 1-quart fruit jar with a tight lid. So assuming the same level of continuous activity, so instead of a treadmill, he's like running around the jar, will the cockroach consume more than 20%? We're going to forget about that idea. We're going to just assume we're talking about the amount of oxygen in the container. Will consume more than 20% of the oxygen in a 48-hour period, and assuming air is 21% moles percent oxygen in the container. Okay, so let's get a rough idea of how we're going to approach this one. So we're going to say during 24 hours. So during, not 24 hours, excuse me, 48 hours are 1.71 times 10 to negative 4 moles of oxygen. And again, this is based on 48 hours. So this is the oxygen it consumes per hour over 48 hours. And if we take a look at that, we will get, what did I do with that? 0.00821 moles of oxygen consumed. So that's how much it would consume. There's more information that we need here, so we have to figure out the size of the container and how much oxygen is in there. So we know it's going to consume that much. Let's go back and see how much it consumes. So I have to do a little bit of background information here. I've got this quart container. I'm going to multiply that times 0.946 liters for every 1 quart. That's the conversion. And within that container, 21% of it, moles, is oxygen. So 0.199 liters of oxygen is available. Now, if I solve for the actual moles in the container using PivNert, I grab all the other variables that are within here that it tells me. I know it's 1 atm. I now know the volume, 1.99 liters. R value is a constant, and the temperature is stated as 297 Kelvin. And if I do that, this is how much oxygen is actually available. 0.008114 moles of oxygen. This is tragic. So I know, take a moment if you need. This is how much oxygen is available. This is how much the little guy needs. If you do the math here, it's not enough. So our little guy is just a few minutes shy of making it. So I know that's pretty rough. So take a moment if you need, and come back when you're able. All right, if you're able to move on, we're going to continue on the notes and do a little sort of a story time little thing here. A gentleman named Evalinsa, I'm saying that wrong, Evalinsa something Torricelli. So anyways, Torricelli. He's running this experiment. He's trying to pump water from a barrel up to a higher elevation. So he's not doing it from the ground up. He's pulling the water up in a tower. So it's kind of think of it like a straw. So he's working from the top, trying to pull the water up from the barrel. And he realizes he can only get the water to rise so high up in the pump. And specifically, he varies a bunch of things on there. He can only get the water to go up so high. So let me write a couple things down here, and then we'll continue. So he pumped water to a maximum height of, staying in the metric system, 10.3 meters. That's just under 34 feet. And he varies the experiment around, and that's as high as he can get the water to go. No matter how strong of a pump or change in the diameter of the pipe, it can only go this high if he's, now you can push the water up from the bottom, but it can only suck the water with the pump so high up from the top. So there's like, think of it as like a vacuum almost within the container, the straw, the pump, whatever. And that's as high as water will go. So he decides, let's take this inside. He's going to change out the water for mercury. Some meters. And so he replaced the water with mercury. It's much, much more dense. And he could pump, if you will, to a maximum height of, and see if you can predict that number, 760 millimeters of mercury. Maybe you remember that from last year, which is something we refer to as like a barometer. And again, he repeats this experiment over and over again. And so he's pulling water, or in this case, mercury, up a straw, if you will, a container, a pump. No matter what, on this specific day, he's only able to raise the level up this high. And what he discovers, the punchline here, if you will, is that the atmosphere is pressing down on the dish of mercury, pushing it up the pump or straw this high. Now, it does vary day to day based on the atmospheric pressure, but this is kind of the ballpark average, if you will, the number that we kind of just go with. And what that kind of establishes is something we call a barometer. Barometer. So that's what we use. Now, something of a slightly different name is something called a manometer. A manometer. And what that does measures pressure of an enclosed gas. So removing the atmosphere from the equation, or yes and no. Comparing the pressure of an enclosed gas to the atmosphere. And I'll give you a little scenario. So again, full disclosure here, I am a terrible drawer, which is why I avoid it if I can. If I have mercury and I pour it into this container, of course, I don't know if you know this or not, it's going to find its level on both sides. It's going to be the same. And if I have an enclosed gas over here, so let's just kind of make a little container. This is supposed to be like a sphere. Doesn't really look like it. So you've got a gas sitting in here and it's pushing pressure out. Say I had a reaction go on and it's pushing pressure out. And I've got atmospheric pressure pushing down over here. So there's like a battle going on. The atmosphere pushing here and the gas is pushing here. If there's a difference, and I'll just focus on the difference, I'll raise this up a little bit. And I'll say, okay, so this is now here and this is up here. Atmosphere, and I'll say gas. So clearly the gas is pushing down, and this is the height difference between the two. So what is the pressure of the gas? Well, the minimum of the pressure of the gas is going to be the atmospheric pressure. So the gas is pressing more strongly down. It pushed it down. So it's beating the atmospheric pressure plus whatever height this is in millimeters. So if this is 760 and I don't know, we want to call us 10, the total pressure of the gas would be 770. And of course, this could go the opposite direction if the atmosphere is pressing more than the gas. So it could go in either direction. Easy enough. All right, let's change or add to this conversation a little bit. We will talk about Dalton. You may remember him from last year a little bit, talking about his postulates on kinetic molecular theory. Dalton's law of partial pressures. He states that the total pressure is the sum of all the individual partial pressures, which is kind of neat. If you don't think it is neat yet, you will soon enough. You know what? I'm going to leave this as a pause because we're like 11 minutes in here, and I think it'd be better to kind of bring this on into the next lecture.